Okay, I'm ready.
Ready? Okay. So,
Mhm.
yes, it's 29 according to my clock. We can start our next speaker after listening to some number theory in Canada. We will now move to the opposite spectrum of the Americas, and we will listen to some number theory in Argentina. So our next speaker is Maria Chara from the Universidad Nacional del Litoral, and she will tell us about a conorm code of an AG code. So go ahead.
Well, thank you. And I want to thank you also, the organizers of this session, for inviting me to talk. And I hope that this topic will not be too far from your interest. This is a joint work with Ricardo Podestá from Universidad Nacional de Córdoba here in Argentina, and with Ricardo Toledano from my university. So I will start talking a bit, recalling some definition about coding theory. What a linear code is, it's just a linear subspace of FQ to the n, where FQ is just a finite field. And we call n the length of the code, the length of the words in the code. K is another important parameter, is the dimension as a vector space of the code. And D is the minimum distance, which is the minimum amount of different coordinates when we look into two different words in the code. And this K and D are important, since K measures the amount of information that you can send, compare with the length of the entire word that you are sending, the n minus k symbols that you are putting to add redundancy. And D is the parameter that tells you how many errors your code can correct. So when you are working with this kind of codes, with linear codes that are the ones that interest to me, you want to have a bigger, a big K and a big D, but you have a bound that says that the sum of these two parameters is bounded by the length plus 1. So you have to try to find some kind of balance between having big dimension and big minimum distance. But we work with AG codes, or codes coming from algebraic geometry. And to construct these codes, you start with the function field and with n rational places on that function field. You could think that these P1, Pn are pairwise distinct rational points on a projective and non-singular and irreducible curve. And you have to choose these two divisors. One is the sum of these points or these places, and the other one is another divisor of the function field, such that the places in the support of this divisor has no intersection with the support of D. So the code is made evaluating functions from the Riemann-Roch space associated to G on these places P1, Pn. And since these places are rational places and F has no poles in any of these points, then this evaluation gives you a vector in FQ to the n, so it's a word there. And it's also a subspace of FQ to the n. You don't know what this Riemann-Roch space is, you can think that we are just like making a generalization of the space of polynomials, and instead of rational points, we are evaluating rational functions, but we only allow poles to happen in places that are on the support of G. It is known that the parameters of this algebraic geometry code are, well, n, which is the length, is just the amount of places that we have on D. The minimum distance is bounded by below by n minus degree of g. This is because the minimum distance is exactly the same as the minimum weight, which are the non-zero coordinates of a word. And since the amount of poles and zeros of a function is the same, then in the worst case, a word can have at most degree of g zeros, so it has to have n minus degree of g non-zero coordinates. The dimension of this code is the dimension here, the small l represent the dimension of the Riemann-Roch space of this divisor G. So the dimension of the code is the dimension of the Riemann-Roch space of G minus the dimension of the Riemann-Roch space of G minus D. But in the case that the degree of this divisor is bounded by n, in this case, we said that the code is a moderate AG code, then this divisor G minus D is a negative one. And so this space is just zero, this dimension is zero. So we have that the dimension of the code for moderate AG code is exactly the dimension of the Riemann-Roch space. And we can use Riemann-Roch theorem to bound this quantity by degree of G plus 1 minus the genus of the function field. If in addition we have the degree of G is not only bounded by n, but is also greater than 2 genus minus 2, then we said that the code is a strong AG code. And in this case, we have that the Riemann-Roch theorem holds with equality, and we have exactly the dimension of the code. So what we did in this work is to use the corner divisor of a divisor considering an extension, and to start with an AG code in some function field and to construct a new one in an extension field. Here the general setting are that we have f, oh, why can I not write? We have f, a function field over the finite field fq, and we have an extension f prime that can be considered over the same finite field or over some other extension, fq of t. And in this case, the corner of a place is defined as the sum of all the places above the original place. Here we have P, and above P we have P1 prime, P2 prime, Pn prime. So the corner is the sum of all of these places above P multiplied by the ramification index E. And this can be extended also for any divisor A, because the corner of a divisor is just the sum of these coefficients multiplied by the corner of the place. So we start with a function field and an AG code on that function field, and we choose an extension, a finite field extension, such that for all the places in the support of D, this is this divisor that we are going to evaluate our functions. We require to have an extension such that for every place here in D, all the places above are rational. Actually, we can define this corner code using just the ones that are rational and not requiring to have all of them. But in the examples that we were interested, we always have that in that extension we had a lot of rational places over our places. So this was just enough. So you pick an extension where this happens, and you define D prime as the sum of all of the places above any place of the divisor D. and G prime to be the conorm of the divisor G. Of course, if you are in if your place is in the support of D splits completely in F prime, then D prime is going to be exactly the conorm divisor of D. But if you have, for example, totally ramified places, then it is not going to be the same. And having this, the conorm code is just the algebraic geometry code or the evaluation code associated to these new divisors D prime and G prime. And since the Riemann-Roch space of G, which is the divisor on S, is contained on the Riemann-Roch space of the conorm of G, then our original code C is a subcode of the new one. So what about the parameters of these new codes? If we consider that C is the original code with parameters N, K, and D, and now we have our new code C prime with parameters N prime, K prime, and D prime, then of course the length of this new code is going to be between N and N times M. M here is the degree of the extension. We are in the case of where N prime is exactly N, if we have that all the places in D are totally ramified in F prime. And we are going to have that N prime is N times M if all the places in D are splits completely. The bound for the minimum distance is just the same that it is now. This is exactly the same as degree of G prime. And if the new code is a moderate HG code, then we can bound the dimension of the new code by this quantity. And we can also use the Hurwitz genus formula to change this G prime, which denotes the genus of the function field F prime, and to put something which is in terms of the genus of the original function field, the one in the bottom. So here we see that we have these quantities minus something which is the degree of the different exponent, and this is more or less counting the amount of ramification that we have in the extension field. So we see that if we want to get a bigger K prime, a bigger bound for K prime, then it is natural to think that, well, what happens if this different is really, this degree of the difference is really low, or if it is zero. So in the case of unramified extension, where not ramification happen at all, we have, well, in this result, we are considering function fields over the same finite field, FQ. So here we have that F prime is an extension of a function field F. But if this extension is unramified, so there are not ramified places here, then what we have is that if we have a code in F, which is a strong HG code, then the conorm code is going to be also a strong HG code, and vice versa. And what we get in this setting is that we are not getting anything new for the dimension, because the new dimension is going to be m times the previous dimension, but this, which is the transmission rate, which is the equation between the dimension and the length of the code, is exactly the same. So we are not getting a bigger information rate when we go to see a conorm code. But we could improve the minimum distance if we know that, for example, the minimum distance of the original code is exactly n minus degree of g. Remember that we always have that d is bigger or equal than this quantity. So another interesting thing that happens in unramified extensions is that if the degree of the extensions is coprimed with Q, then the dual code of the conorm code is exactly the conorm code of the dual code of C. Here, the dual code is just the orthogonal complement of the code C in SQ to the N with the standard inner product. So if we have this kind of unramified extensions in which the degree of the extension is coprimed with Q, we have this result. And we think that this could be true also in a more general setting, because from the proof of this result, what we get is that the dual of the conorm code can be represented as an evaluation code using this divisor G, where here this is the divisor of some specific Veil differential, and the conorm of the dual is more or less the same, where here we have the conorm of another Veil differential, the conorm divisor of another Veil differential. So if we can prove that this conorm is exactly this other divisor, or if it is rational equivalent, then we will have that this equality holds in a more general setting. But we do not expect that this is going to happen in all the cases, because we have an example using Hermitian codes in which the conorm of the dual is different from the dual of the conorm. Another interesting case is when we consider the other case in which we have a lot of ramification in the extension. But before I talk about that, I want to recall what a cyclic code is, because actually all of this work was motivated for this cyclic codes. We were working with cyclic codes trying to represent as an algebraic geometry code any cyclic code, and trying to see what condition we have to put on a cyclic code to be represented as a rational one, what has to happen. And a cyclic code is just a code in which is closed under the cyclic shifts of coordinates. That is, if this is a word in our code, then if I move this last coordinate and put it in the front, then what I get is a new word which is also on the code. And if I continue doing that, putting C n minus 1 in the front, then I get another code word. And that's happened for all the movement that I can do in all the words. And what we get in this case is that we were considering extensions f prime over f, both of them to be function field over the same FQ. And we we choose code C such that D has only totally ramified places. So over any of the places in D, we have only one place in the extension. Then the first thing that one can see very easily is that if the conorm code is a cyclic code, then the original code was cyclic. And the more important thing is that if the extension is Galois of degree m, and m is coprimed with Q, or Q divides m, and we are in this setting where D has only totally ramified places in its support, then we have that the conorm code is cyclic if and only if the original code was cyclic. And not only that, we can see on the proof of this result that what we get actually when we construct this conorm code is a different representation of the same code C in a function field with bigger genus. So that's why I said that this whole work was motivated by trying to see how to get different representation of a cyclic code in a function field with a bigger genus. So with this, we could see that many classic codes can be seen as conorm codes. We have a representation of these codes as conorm codes. For example, if we have the repetition code, which is really ASA, it is just repeating n times the same symbol. Then if the length divides q minus 1, we can represent this repetition code as a conorm code. For emission codes, here we are thinking on f is just the rational function field over fq squared, and f prime is now an extension where y satisfies that y to the cube plus y equals x to the cube plus 1. And we put we have a code here C, and the conorm code we call H here in the extension. The code C is formed using all the rational places in F, except the P infinity, which is the pole of X. And we use that place to make the divisor G. So here we have that this code is dg, where G is Q P infinity, for example. Then the emission code with the conorm code of this one is exactly what is known as the emission code. So the emission code can be represented also as a conorm code. And I'm more interested example is the example of Reed-Solomon codes, because any conorm code can be represented as any Reed-Solomon code can be represented as a conorm code. The Reed-Solomon codes are just evaluating polynomials up to degree k in q minus 1 element of fq except the 0. And these codes are all cyclic codes, so we can always have a representation of these codes as rational codes in the rational function field, and then using the conorm code, we can have the representation of this same code in a bigger genus. So we think that maybe this could be useful for code-based crypto. We don't know yet. We have to study more. We know that there have been some attacks for some crypto system using MAC-least encryption, using codes first for codes represented in function field with lower genus, but then they also could break the security in higher genus. But the general problem is still open because they cannot handle subfield subcodes, and so maybe this could be good or not for that. And well, we have to work more. And thank you very much. Gracias a todos.
Muchas gracias, María, para la charla. Thank you very much.